In many astrophysics classes, black holes are left for the end of the course. I think that's a terrible idea. It's educational malpractice. Black holes are some of the most fascinating things in the universe. They're the reason why many of us got into astrophysics in the first place. That's certainly the case for me. I was 7 years old when I saw the Disney movie, The Black Hole. The story is ridiculous, but I was captivated by the idea of a black hole. The more recent movie, Interstellar, from 2014, might be having a similar effect on today's young people. So I can't resist jumping ahead and talking about black holes. First, though, is a prologue about the gravitational field of a spherical object. Newton's law of gravity, F equals gmm over r squared, gives the magnitude of the force between two masses. Strictly speaking, it's the force between two point masses, two idealized mathematical points with non-zero mass but zero size. Last time, we talked about what happens when we allow the body feeling the force to have a non-zero size. It feels tidal forces, differential gravitational forces that tend to pull the body apart. Now, let's talk about what happens when we allow the body producing the force to have a non-zero size, like the Earth. The Earth isn't a point mass, it's a sphere. When we're standing on the surface, our bodies are gravitationally attracted to every cubic centimeter of material in the entire Earth, pulling all at once. And the rock just below our feet is much closer to us, so it pulls harder than the same amount of rock does on the other side of the Earth. So you might think it would be a big mess to try to calculate the net force from the entire Earth. You'd have to add up the forces exerted by each cubic centimeter, taking into account the huge variations in distance and direction from place to place. But one thing Isaac Newton taught us is that when you're outside a spherically symmetric object, you can calculate the gravitational force by pretending it's a point mass that's endowed with the total mass of the real object. This is not obvious. It's another one of those things that took Newton years to prove. That's why we've been blithely writing F equals gmm over r squared, even though planets and stars are not point masses. Even more amazing, though, is what happens if you're inside an object with a spherically symmetric mass distribution. Say you dig a tunnel into the Earth, down to a radius r from the center. It turns out the net gravitational force at the bottom of the tunnel can be calculated by pretending all the mass down deeper, with radius less than r, is replaced by a point mass at the center. You can ignore all of the exterior mass. To bring home how remarkable this is, imagine you're inside a hollow spherical shell of matter, as though the Earth had a central cavity. You would feel no gravitational force. You'd be weightless anywhere in the cavity, even right up against the wall. The point is that although the nearby atoms are pulling harder, there are more atoms farther away pulling in the other direction, and the effects cancel each other. Now, the real Earth doesn't have a hollow cavity. If we were inside the Earth, we would feel a gravitational force, which we can calculate by pretending all the interior mass is concentrated at the center. If the Earth had a constant density, rho, then the total interior mass would be 4/3 pi r cubed times rho. And the gravitational force is proportional to the interior mass divided by r squared. So it goes like r cubed over r squared. It's proportional to r. So as we dig further down, the force declines in strength, and at the center of the Earth, there's no gravitational force at all. Now, on to black holes. A black hole has no surface. It's a real-life point mass. The mass really is concentrated into a single point in space. So as you approach, the gravitational force gets stronger, without bound, all the way down to r equals 0, where it becomes infinite. A black hole is an infinitely deep gravitational pit. And as we'll see, the pit has slippery sides. If you get too close, you inevitably fall in. Let's say we're cruising around the galaxy, and through some careless navigation error, we find ourselves at a distance r0 from a black hole. In a panic, we turn away from the hole and fire our thrusters, burning all the fuel in a desperate burst, giving the spaceship a velocity v0 directed away from the hole. Will we escape? We can figure that out based on the conservation of energy. The initial energy of the spaceship is the kinetic energy, 1/2 mv0 squared, plus the gravitational potential energy, minus g times big M, little m, over r0. Here, big M is the mass of the black hole, and little m is the mass of the spaceship. At some later time, we managed to make it out to a larger distance, r1, with a slower speed, v1, since the black hole's gravity has been slowing us down. So now the energy is 1/2 mv1 squared minus gmm over r1, which we can set equal to the initial energy. Let's think about the case in which we just barely escape. In that case, r1 approaches infinity and the potential energy approaches 0. In addition, v1 approaches 0 because we had just enough energy to make it out with no leftover kinetic energy. So the total energy in this case must be 0, giving us a simple equation which we can solve for v0, giving the square root of 2g big M over r0. That's the formula for the escape velocity. If we have enough fuel to go at least that fast, we escape. Otherwise, we fall in. And as we fall in, we curse our navigator for getting us into this mess and our chief engineer for not having enough fuel on hand. But here's the thing about the black hole. Since there's no surface, there's no minimum value for r0. There's nothing equivalent to the Earth's surface within which the gravitational force starts getting weaker. So the escape velocity grows without bound as r0 approaches 0. And at some point, the escape velocity exceeds the speed of light, the fastest speed it's possible for anything to attain, and in that case, no amount of fuel would have been enough. To find the value of r0 where that happens, we set the escape velocity equal to c, the speed of light, and solve for r0, giving 2gm over c squared. So even though the black hole itself has 0 size, 2gm over c squared is a sort of a radius. It's the radius of no return. It's called the Schwarzschild radius after Karl Schwarzschild, the first person to solve Einstein's equations of general relativity exactly for the case of a point mass. Another more evocative name is the event horizon. From beyond that horizon, no light can reach you, so you can't see any events that might be going on there. Speaking of general relativity, we didn't use it in our calculation. We've used Newton's law of gravity and Newtonian equations for the kinetic energy and potential energy. In Einstein's theory of gravity, which is more accurate than Newton's, those expressions don't hold. So, does that mean our calculation of the Schwarzschild radius was bogus? Well, in a sense, yes. Anytime we're dealing with strong gravitational fields and speeds approaching c, we shouldn't expect to get the right answer with Newtonian physics. So, I could spend the next 16 lectures teaching general relativity. We would talk about the curvature of space-time, covariant and contravariant tensors. We'd have a grand old time. But then there would be no time for all the other wonderful things I want to share with you. So, we'll enjoy some doses of relativity on occasion, but we can't dive deeply enough to perform this calculation correctly. So I'll just tell you the answer. The exact answer comes out to be 2gm over c squared. It's the same as our result, which is a mild coincidence. We might have expected the exact answer to be some number times gm over c squared, because the only relevant physical quantities are g, m, and c, And that's the only way to combine them to give something with a unit of distance. But it is a coincidence that the number multiplying gm over c squared is 2 in both the Newtonian and the relativistic calculations. Let's find the Schwarzschild radius of a black hole with the mass of the Earth. In that case, m is 6 times 10 to the 24 kilograms, giving a Schwarzschild radius of 9 millimeters. What that means is that if we could somehow compress the entire Earth down to the size of a marble, we'd have ourselves a black hole. For the mass of the Sun, the Schwarzschild radius comes out to be 3 kilometers. So we can write that formula as a scaling relation. Rs equals 3 kilometers times m over m Sun. Now let's imagine that some malicious aliens arrive in the solar system and they compress the Sun down to a radius of 3 kilometers, turning it into a black hole. What would happen to the solar system? How long would we have before the Earth fell into the black hole? Actually, the Earth wouldn't fall in at all. The planet's orbits wouldn't change. The solar system would be a lot darker and colder for sure, but the planets would continue on their usual orbits. It's a corollary of Newton's theorem about spherically symmetric mass distributions. That turns out to hold true in relativity too. The force from the Sun is the same as the force from a black hole of equivalent mass. So in the popular imagination, black holes are like vacuum cleaners, sucking up everything around them. That's not quite true, or at least it's no more true than it is for the Sun. The Sun doesn't suck in all the planets. To fall into the Sun, or a black hole, you need to have nearly zero angular momentum, hardly any transverse velocity, so that you follow a radial trajectory all the way down to r equals 0. We'll see later that black holes do swallow things. We have excellent evidence for luminous hot vortices of material spiraling into black holes. But that only happens when there's some way for the orbiting material to get rid of its angular momentum. Another thing I want to emphasize is that black holes exist. They are not just a plot device in science fiction movies. Recent discoveries, especially the detection of gravitational waves, which we'll come to later, do not leave much, if any, room for skepticism. They are out there. Let me show you some evidence for a black hole that we can understand quantitatively based on our studies so far. We start with an image of the Milky Way, our own galaxy, which appears as a band of light reaching across the sky. We zoom in on the center of the galaxy in the direction of the constellation Sagittarius, revealing that the smooth band of light is actually the summation of the light of hundreds of billions of distant stars. The black blotches are clouds of gas and dust in the foreground, blocking our view. If we keep zooming in, we eventually arrive at a cluster of bright stars near the center. A group at UCLA, led by Andrea Ghez, has been watching these stars since the mid-1990s. They're moving fast, and not just in random directions. The stars are being deflected by the gravity of a giant mass in the center of the image. Some of the stars are orbiting the center in Keplerian ellipses. There's one star in particular, named S0-2, that made a complete orbit over the last 16 years. But here's the thing. In optical and infrared images, there's hardly any light coming from the focus of the ellipse. SO2 and the neighboring stars are being attracted to a seemingly unremarkable spot in the image. Let's figure out how massive the attractor must be based on observations of SO2. The images show that the angular size, delta theta, of the long axis of the ellipse is about 1/4 of an arcsecond. And we know from other observations that the distance, d, to the galactic center is 8 kiloparsecs. With that information, we can calculate the semi-major axis A. Delta theta equals 2a over d, implying a is 1/2 delta theta times d. That's 1/2 times 1/4 of an arcsecond times 8,000 parsecs, which, from the definition of parsecs, is 1,000 AU. We also observe that SO2 takes 16 years to go around. That means P equals 16 years. And whenever we know both P and A, we can apply Kepler's third law to find the mass. First, let's rearrange Kepler's third law to solve for the mass. M equals 4 pi squared over g times a cubed over p squared. And at this stage, we could plug in the numbers, looking up the numerical value of g, converting a into meters, p into seconds, and so forth. But let's make life easier by converting the equation into a scaling relation. We see that m is proportional to a cubed over p squared, and we also know the answer is 1 solar mass for the Earth. So we can write m equals m sun times a over 1 AU cubed times p over 1 year to the -2 power. That's more convenient for our problem because we already know a and p in those units. The mass of that mysterious attractor in units of solar masses is 1,000 cubed over 16 squared, which is 4 million. Wow. So lurking at that nondescript spot in the image, which has the official name Sagittarius A star, is something with a mass of 4 million suns. And it's all crammed into a space that must be smaller than SO2's distance of closest approach, which is about 100 AU. That's not much bigger than the solar system. So think about 4 million suns, all within the solar system. Astrophysicists have not been able to think of anything that could have so much mass within such a small space without either glowing very brightly or quickly collapsing under its own gravity. So it's either a black hole or something even more exotic beyond our current physical understanding. How close are those stars getting to the Schwarzschild radius? Are they in danger of falling in? Let's see. The Schwarzschild radius is 3 kilometers times m over m sun, which in this case is 3 kilometers times 4 million. That's 12 million kilometers, which might sound big, but it's only about 1/10 of an AU. The orbit of our friend SO2 has a minimum distance of 100 AU, so it's perfectly safe. Every once in a while, though, a star or a cloud of gas will fall into the hole. Last time I described the evidence for tidal disruption events. They take the form of bright outbursts from the centers of distant galaxies. But those galaxies are all so far away that our telescopes can't resolve the details. There's no hope of making images that show the star falling in. But what about our own Milky Way? Maybe closer to home, we could watch a star getting torn into shreds. Let's figure out how big a telescope we would need. Remember, the fundamental limit on the angular resolution of an image, delta theta min, is the diffraction limit, which is on the order of lambda over d, where lambda is the wavelength of light and d is the diameter of our telescope. So how big of a d do we need to resolve details on the scale of the Schwarzschild radius, 0.1 AU? We can find out by setting lambda over d equal to the angular size of the Schwarzschild radius. That's 0.1 AU divided by 8,000 parsecs, the distance to the galactic center. For lambda, let's insert 0.5 micron, typical of visible light. After all of the necessary unit conversions, the diameter of the telescope comes out to be 8,000 meters. Whoa! The world's largest optical telescopes are 10 meters across, and here we need one 8 kilometers across. That sounds crazy, and it is crazy. But nevertheless, there's an effort underway to make images sharp enough to resolve the Schwarzschild radius of Sagittarius A star. The trick is to use a radio telescope instead of an optical telescope. The project is called the Event Horizon Telescope. Radio telescopes rely on detecting radio waves, which are a type of electromagnetic radiation, like light, but with longer wavelengths. The Event Horizon Telescope observes at a wavelength of about a millimeter, 2,000 times bigger than the wavelength of visible light. That sounds bad. The minimum telescope diameter is proportional to lambda. So instead of 8 kilometers for an optical telescope, now we have to build a radio telescope 16,000 kilometers across. That's comparable to the diameter of the Earth. And yet, it can be done. At radio wavelengths, it's possible to combine the information from widely separated telescopes to mimic the performance, in terms of angular resolution, of a much larger telescope. We'll see how this works in a later lecture. The diffraction limit, in that case, goes like lambda over b, where b is the distance between individual radio telescopes, rather than the diameter of any one of them. So if you connect telescopes in different parts of the world, you can get the necessary angular resolution, at least in principle. This technique is called very long baseline interferometry, and it's become routine for observations at wavelengths of meters and centimeters, but getting it working at a millimeter is still a challenge. Soon, though, I hope we'll be enjoying images from the Event Horizon Telescope. Let's go back to the question of what it's like to orbit a black hole. We've seen that if you get too close, within the Schwarzschild radius, you fall in. And if you're very far away, the orbits are the same as they would be around a star or a planet or any normal astronomical body. What I want to discuss for the rest of this lecture is what happens in between those extremes, when you're orbiting near a black hole, but not right at the Schwarzschild radius. To answer this question, we'll use the effective potential energy, a concept we used earlier to analyze planetary motion. We wrote the total energy in the form 1/2 mvr² plus U effective, where U effective is the sum of the real potential energy minus gmm over r, plus a term that depends on angular momentum, L² over 2mr². That L² term is the kinetic energy associated with angular motion, but because angular momentum is conserved, we were able to write it in a form that depends only on r, making it resemble a type of potential energy. The point of all this is that it gives us a graphical way to understand how the radial coordinate changes with time as a body whirls around an attractor. What happens in general relativity is that you get an extra term in the effective potential energy, minus L² times the Schwarzschild radius over 2mr². So now there are 3 terms. When we replot U effective for a black hole, we need to add the contributions of the -1 over r term, the +1 over r² term, and the -1 over r³ term. As r gets smaller, that new 1 over r³ term grows the fastest of all, and it's negative. So the effective potential dives downward at small radius. To make the numbers come out nice, the vertical axis shows U effective divided by little mc², and the horizontal axis shows the radius in units of the Schwarzschild radius. And for concreteness, I chose a value of the angular momentum equal to 2.1 little mc times the Schwarzschild radius. What we can see is that below 1 Schwarzschild radius, there's a pit in the potential. Remember, we can visualize what's going to happen to the radial coordinate r by imagining we drop a marble onto the curve starting from an initial height, E, given by the total energy. If we're far away from the Schwarzschild radius, the marble rolls back and forth. That means R oscillates back and forth, as was the case in Newtonian gravity. The particle follows an orbit with some minimum and maximum distance. But if we let go of the marble inside the Schwarzschild radius, it falls into the pit, regardless of energy. That's consistent with what we learned earlier. If you're inside the event horizon, you're doomed. And even if we start the marble farther out in the bowl, if the energy is high enough, it won't just roll back and forth. It'll go over the inner wall of the bowl and fall into the pit. What that means is that in general relativity, you can hit the origin even if you have some non-zero angular momentum. There's no more barrier here that seals off the singularity as there was in Newtonian gravity. It's as though when you get close enough, the hole reaches out and grabs you. It absorbs both your mass and your angular momentum. That's right, black holes can rotate. It's pretty weird, a rotating point mass. I drew this curve for a specific value of angular momentum, and different values lead to different shapes for the bowl. Let me now show you what happens as we lower the angular momentum. The bowl gets pounded down on the left side until it's not even a bowl anymore. There's no more minimum. That means there's no place where the particle can sit still at a constant radius. A circular orbit is impossible. This is a famous result in general relativity. It's called the ISCO, the innermost stable circular orbit. The ISCO, for a non-rotating black hole, turns out to be 3 times the Schwarzschild radius. For a rotating black hole, the ISCO can be larger or smaller depending on which way it's rotating. Let's go back now to a case with more angular momentum, so the effective potential energy curve still looks like a bowl. If you give the particle a modest amount of energy, the radial coordinate oscillates back and forth just as it does for a planet going around the sun. For a planet, we found the trajectory is an elliptical orbit with a minimum distance of a times 1 minus e and a maximum distance of a times 1 plus e. But remember, you only get ellipses for that very specific case of a force that goes like 1 over r squared. And in general relativity, the force doesn't go exactly as 1 over r squared. There's that extra term in the potential. So you don't get perfect ellipses. Close to the black hole, the orbits aren't even approximately ellipses. They're rosettes, like the ones I showed in the last lecture, whipping around fast as they approach the black hole, then slowing down as they recede and coming back again from a different angle. If you're relatively far away, the orbits are very nearly ellipses, but not quite. What happens is, the orientation of the ellipse gradually wheels around in space. It's an effect called apsidal precession. Do you remember the eccentricity vector? That strange combination of velocity, momentum, and position that turns out to be conserved in classical gravity? What happens in general relativity is that E vector is no longer conserved. It slowly changes with time, rotating around the direction of the angular momentum vector. So, if you looked carefully enough at planets orbiting a black hole, you'd see they're not quite obeying Kepler's first law. And it's not just black holes. Remember, once you're outside a spherical mass distribution, the gravitational effects are the same no matter whether you're orbiting a planet, a star, or a black hole. That means Kepler's first law must be at least a little bit wrong in the solar system, too. The planetary orbits should be precessing. And they are. The effect is strongest for Mercury, the planet with the smallest orbital distance. In fact, the precession of Mercury's orbit has been observed for centuries. But it's precessing mainly for a different reason. the gravitational forces from all of the other planets pulling on Mercury also causes a departure from the idealized problem of one star and one planet, and that causes precession too. But the observed precession is slightly faster than Newtonian theory said it should be. Theory said the major axis should rotate at a rate of 5,557 arcseconds per century. But the data showed the precession is faster than that, by 43 arcseconds per century. Albert Einstein knew he was onto something when he realized in 1915 that his theory predicted an extra boost to the precession rate of 43 arcseconds per century. He solved the long-standing problem of the anomalous precession of Mercury. Here's a quote from his biographer, Abraham Pais. "This discovery was, I believe, by far the strongest emotional experience of Einstein's scientific life, perhaps in all of his life. Nature had spoken to him. He had to be right. When he saw that his calculations agreed with the unexplained astronomical observations, he had the feeling that something actually snapped in him." There's so much more I'd like to tell you about black holes. We're out of time for this lecture, but don't worry. This isn't the last time we'll encounter black holes in our astrophysical tour of the universe.